It's my pleasure today to introduce Professor Andrew Bunker from University of Oxford. So Andy did his PhD in Oxford in 1996. Then he moved to Berkeley as a postdoc, and then to Cambridge for 5 years as a postdoc as well. Then he obtained a faculty position at Exeter before becoming the head of astronomy of the Anglo-Australian Observatory. And then in 2008 he became a reader in astrophysics at the physics department of Oxford University, and is now a professor in Oxford University. His main interest is the first galaxies. He's a member of the NIR Spec GTO team, and he's a PI of an ERC. I don't have the name of the ERC.
First galaxies.
He's the first galaxy. And today he's going to talk about JWST at the edge of the universe, finding galaxies in the epoch of reionization with NIR Spec.
Well, many thanks, Nicola. And it's a great pleasure to be back in Cambridge. I spent 5 very happy years here around 2000, and I worked with a lot of people, with Richard McMahon and our student at the time, Elizabeth Stanway. We were finding the first few redshift 6 galaxies. And with Ian Parry, we were doing the first multi-object infrared spectroscopy on large telescopes from the ground. And I've carried those interests forward. And now I'm going to talk today about doing multi-object spectroscopy from space, also in the near infrared, using James Webb Space Telescope. And unless you've been living in a cave, you'll realize that James Webb launched Christmas Day 2021, and very successful launch from French Guiana, and really spectacular. I joined the team for the NIRSpec instrument, the near-infrared spectrograph, back in 2004, and we were told at the time we were 3 years before launch. It was quite a long 3 years, but when it did launch, it's been absolutely spectacular and really delivered. And then this was the iconic photo from the nose fairing, where pretty late on in the process they installed a camera. You can see JWST, which looks like it's covered in tin foil, separating, and then a few seconds later the solar panel popping out automatically. And that, I thought, was the last we'd see of James Webb Space Telescope. But then my colleague Peter Jacobsen, who was the principal investigator for NIRSpec, sent me from his back garden in Copenhagen. He took some photos a few days after launch, and this moving dot is JWST. And you can see it shift relative to the background stars. And in fact, it seems that most of that movement is not actually the movement of James Webb. It's the parallax of Copenhagen as it goes round. But that's pretty cool. That was 16th magnitude at that point. So James Webb is revolutionizing many fields of astrophysics. I'm going to focus on the high-redshift universe, which is my own field. And almost every conference I go to, there's some obligation to show this plot. If you're an extragalactic astronomer, apologies, because you've seen this a million times, but it does sort of shape where we were in our understanding until quite recently. So on the x-axis we have redshift. So we are here, redshift 0 today, and we're trying to push back to redshift 8 and beyond. That's within the first billion years of history. And what the y-axis purports to show is the star formation rate of the universe, and that's normalized per co-moving volume. So that's a frame which stretches with the expansion of the universe. So pretty much think of it as how exciting a place to live in the universe was as a function of time. So it seems today it's pretty quiet. You know, we know star formation is ongoing, including on our Milky Way, but there's not much. If we go back a few billion years, when the universe is about half its current age, we have star formation rates which were more than an order of magnitude higher volume averaged in the universe. Then if we go even further back in time, possibly seeing the epoch of the first few galaxies to form stars, that then drops again. And this is called the Lilly-Maddow diagram. Simon Lilly, Piero Maddow came up with this about the same time in the mid-90s, based on a combination of Hubble Space Telescope data and ground-based data. And this has sort of plagued astronomy for a few years because there's a few selection effects going on. So the left-hand side of the plot in red, star formation rates are usually determined from the Balmer recombination lines. That's H-alpha. It tells you pretty directly the number of ionizing photons there are. Where do the ionizing photons come from? They're from the most massive, shortest-lived and crucially hottest stars. So it's telling you about star formation on a timescale of about 10 a million years or so. The right-hand side shows us our knowledge until recently of the high-redshift universe that was pretty much restricted to the rest frame ultraviolet. The reason for that is the longer wavelengths shifted beyond the bands, the transmission bands in the atmosphere where we were sensitive. So we're using the rest frame ultraviolet. Of course, the ultraviolet is somewhat hard hit by any dust extinctions. You might be underestimating star formation rates. And also, it's not probing exactly the same duration of star formation. And the area in green is the epoch of reionization. So this is beyond around redshift 6, so that's within the first billion years of the Big Bang. The gas between the galaxies, the intergalactic medium, seemed to be mostly neutral after the initial recombination. And it stayed like that for nearly a billion years. And then something around a redshift of 6 fried that gas. There was an influx of high-energy ionizing photons that stripped off the electrons. Where did they come from? So there's a few things on the menu. I'll come back to that later on. But it's a fundamental, literally, phase change of the universe, those redshifts. So I'm interested in finding distant galaxies. How do you do that? So I'm going to give a brief summary of the state of play before James Webb. So when I started my PhD a long time ago, the most distant normal galaxy, non-AGN, was around a redshift of 1 or so. We thought that was exciting. Okay. Now, as time progressed, we pushed that redshift frontier back further in time. And one of the pioneers of this, Chuck Steidel, who worked a lot with Max Spattini, I think in the audience, developed something called the Lyman break technique, where you image in different filters and you identify distant galaxies because they have characteristic colours. So here's a little cartoon I borrowed, I think, from Mark Dickinson. So this is, the yellow is the spectrum, and then these 3 curves are filters. So you can see here that in the red filter, a lot of light. Here you have this sort of weird picket fence-like structure. That is that distant galaxy. The light from that has been travelling towards us and has passed through intervening clouds of hydrogen, the gas between the galaxies. Each of those have absorbed at the various resonant frequencies, Lyman-alpha in particular, and that eats away. And then below the Lyman limit, that's the ionization edge of hydrogen. It's basically illegal to get any photons. The universe mops those up. So if I put a filter here, I see no light. Here, reduced light. Here, lots of light from the distant galaxy. Imagine a lower redshift galaxy. That yellow region shifts to the left to bluer wavelengths. And I would see the lower redshift galaxy in all the filters. So I'm interested in stuff that vanishes at short wavelengths because that's a candidate for being very distant. And Steidel pioneered this at redshift 3, and then a few years later, me and other groups pushed this to redshift 6 and beyond, using infrared filters that started to become available, particularly with the Hubble Space Telescope. So we were successful in identifying candidates first at redshift 6 and then later on out to redshift 9 or so. But you might be a bit cynical. This is just counting red dots in Hubble Space Telescope images. It's great, but is it really scientific? How can I prove these truly are high redshift? So the embarrassing possibility is they might just be intrinsically red sources. You know, possibly even low temperature L&T dwarfs in our own galaxy. Now that would be embarrassing, okay? When you claim the most distant object in the universe and it happens to be red and nearby. Or potentially evolved or dusty galaxies at intermediate redshift. So to really nail this, we need spectroscopy. So finding candidates at very high redshifts, why has it been so difficult to confirm them spectroscopically? So for 25 years, the Lyman break technique has been very successful in getting large numbers of candidates from images, combination from the ground and from space. But at redshifts beyond 6, only a tiny fraction until this year have been confirmed. So why is that? So when you take a spectrum from the ground, you are sampling the rest frame ultraviolet working in the optical and the near infrared. And what was for a long time believed to be the strongest emission line is Lyman-alpha. That's the n=2, n=1 line of hydrogen. And, you know, predictions from decades ago had this having some huge fraction of the power output of the galaxy. But people looked for this for a long, long time, and they typically found either it wasn't there or it was very weak. Why is that? Well, of course, Lyman-alpha, it's tuned to that transition of hydrogen. So if a Lyman-alpha photon forms in a galaxy, it has to play cosmic pinball to get out. It bounces between hydrogen atoms because it just is tuned to promote the electron that then cascades back down and so on. So that can extend the escape path by orders of magnitude. If you have any dust in these galaxies, that can mop that up. So beyond Lyman-alpha, people have really struggled. So people sometimes see one of the carbon lines, but rarely. ALMA has been quite successful in individual galaxies in getting atomic and even some cases molecular lines in the millimetre, sub-millimetre. But really, to change the game, we need access to the rest frame optical in high redshift galaxies, which involves going beyond 2.5 microns, which is where our sensitivity from the ground stops. And we can do that now, thanks to James Webb Space Telescope, and in particular the NIR Spec instrument, which works from between just below 1 micron all the way out to 5.3 microns. So what this plot shows, wavelengths along the x-axis, and your favourite emission lines on redshift here, and your favourite emission lines here. So you can see the H-alpha line, and I said that was kind of a gold standard for measuring star formation rates. You can see that out to redshift 7 or so. You can see things like the carbon lines out to ridiculously high redshifts potentially. And this has suddenly been enabled thanks to James Webb. So there's a number of instruments. I'm going to focus mainly on NIRSpec. I'll introduce that in more detail later on. But we also have MIRI, which was a partnership between a European consortium and NASA JPL. That works in the mid-infrared out to 28 microns. There's a slitless spectrograph built by Canada called NIRS. That's good for finding bright galaxies, but you have a volume-limited sample then. And there's an imager, NIRCam, which is University of Arizona. And after launch, there was about 5 months of commissioning. And then with great fanfare, the first few images were released. And here we see President Joe Biden discovering some gravitational lensed arcs. This was the first image released of a rich cluster called SMACS, some telephone number. And behind that, that was gravitationally lensing a number of high redshift galaxies, amplifying the source. And they also released the spectra. And this is probably a little bit hard to see, but I've got a zoom-in version here. So this is a spectrum, and they've color-coded some lines. This is the first spectrum released from James Webb. And these things in red, these are the Balmer lines of hydrogen. But you have other elements as well. The blue here are some neon lines. Sorry, the green is neon, and the blue is oxygen. What's interesting is you have 2 lines of this oxygen 3. So this oxygen 3 is a very strong line, often 5007, it's a doublet. But very rarely do we see this second line. And this second line comes from the same ionization state, doubly ionized oxygen, but it's in a high excitation level. So if you have this line, called an auroral line, and that line, and the ratio gives you, just from kinetic theory, the temperature of the interstellar medium. And we couldn't do this before, so for the first time we have the measurement of the temperature of the interstellar medium of a galaxy at redshift 7. Now, people got very excited because there were predictions that you could only see this auroral line in stacks of many, many spectra. We're seeing it fairly routinely. It's one in every few galaxies we see this. So it's telling you something about the universe. It's telling you that the gas between the stars was hotter on average in galaxies in the early universe. And of course, everybody jumped on data sets, and there were at least half a dozen papers analysing these spectra, some of which I'm on. And I can give you just a quick potted history of this. So one thing with this auroral line, that enables us to pretty directly measure the metallicities of these galaxies. Previously, people have used so-called strong line ratios, and there's some uncertainty in the calibration, but this removes some of that ambiguity. This shows a plot of the mass of the galaxy in log space along the x-axis, and its metallicity on the y-axis. So metal rich up the top, low metallicity down the bottom. Here's where galaxies today from the Sloan survey sit, and these are where these redshift 7 galaxies sit, and overlaid are some simulations. So what's clear, they are more metal poor. I mean, no surprise, metals are made with time in stars, but the exact evolution of this mass-metallicity relation is still open for debate, and for the first time we are truly constraining it within the first billion years. Another interesting thing, I mentioned we need high temperatures. So Harley Katz put out a paper where these various diagnostic diagrams, typically on the x-axis here, you've got the ratio of this auroral line to the other oxygen 3 line. That's telling you the excitation, the temperature. And then the y-axes of various different line diagnostics. That's telling you about the ionization state, etc. And what's interesting is it's difficult to get these high temperatures just with plain vanilla stellar populations. They're also inconsistent with heating by AGN. You need some other mechanism. I mean, he speculates it might be X-ray binaries, it might be cosmic rays. What's clear is we don't know, and it was unexpected. So those are two fun facts which will probably power astrophysics, or this branch of astrophysics, in the near future. So not only that, early on, the deep imaging that was released in the first few weeks with James Webb was seized on by many researchers to use exactly that Lyman break technique I described, but with longer and longer wavelength filters. So that means higher and higher redshift. And there were claims that came out of populations of redshift 12 to 16 galaxies. And some of these were plausible. Some were due to flux calibration issues early on with the data which have now been resolved. So this was a famous example, a candidate redshift 16 galaxy. Others had suggested that these data points, these yellow things, are the photometry. This green is not the real spectrum, it's a model that fits the data. That in fact this break and these particular things could also be fit at a lower redshift with high equivalent width. So it's very strong emission lines mimicking this break. So in fact a spectrum was taken within the last few weeks, and if you don't want to know the answer, look away now, but the spoiler alert is in this case that galaxy did indeed turn out to be the lower redshift solution. But there have been plenty of galaxies where people have confirmed redshift 10 and beyond, and I'll show you those later on. So there's a number of big questions we might want to address. So what's the history of star formation? That's the McDowell-Lilly diagram I showed. What is that really when we have the same diagnostic over all of cosmic time, H-alpha, for example, all the way to redshift 7? And how is that split between the galaxies as a function of time? We know merging, downsizing, all these jargon words, they play a role, but we can determine that directly now. And we'd like to chart the history of chemistry, the formation of the heavy elements with time. The metallicity, I already showed you the mass metallicity. We can routinely now measure metallicities in distant galaxies. Does that agree with our understanding of the previous generations of star formation? And then finally, the mystery of reionization. What provided those photons, the high energy photons, which fried the gas between the galaxies, achieving this reionization around a redshift of 6 or 7? Where did they come from? Was it AGN? Was it galaxies? And, you know, very simply, all these claims in the literature for the last 20 years of we have found some candidate high redshift galaxies, were people honest? Were they really confirmed? So most of my talk, I'm going to talk about my role in collaboration with a very large team I'll introduce in a moment, on the NIR Spec instrument science team. And having served on this team for many, many years, our team were rewarded with 900 hours of guaranteed time observations. And most of that we've put towards a joint project with our colleagues on the NIRCam team, the imaging, called JADES. And this stands for the JWST Advanced Deep Extragalactic Survey. And there's a huge team. This list was done a year ago, is incomplete, so apologies for people in the audience who aren't on this. I've highlighted the instrument science team members, but particularly want to acknowledge the involvement of many postdocs and students in working extremely hard. And really, since we got the first data in September, it's been non-stop. So NIRSpec works between 1 and 5 microns, and we have different resolving powers. We have a prism, very low dispersion, that gets the whole spectrum at once, but very low resolution. So this is great. We can see spectral shapes. We can see some emission lines. It goes very sensitive. For higher spectral resolution work, we have gratings with resolving powers of 1,000 or 3,000. And these are good for separating lines that would be otherwise blended. For example, the Lyman-alpha, the H-alpha line with the nitrogen 2. That's commonly used as a diagnostic. And at the highest resolutions, resolving power or spectral resolution of about 100 kilometers per second, we can do galaxy kinematics. And we have several different modes this instrument can work in. There's some traditional fixed slits that people, for example, the exoplanet community would be using, look for transits. We have something called integral field spectrograph that carves up a small box, 3 by 3 arc seconds, and takes a spectrum at each point, sampling at 0.1 arc seconds. This is great for rotation curves of galaxies, great for finding extended halos of emission. And then something I'm going to focus on is the multi-object spectroscopy mode. So we have a lot of microshutters. We have 250,000 little doors that we can command open in space. Now, the first rule, usually of a space mission, is have as few moving parts as possible. We've got 250,000. I mean, none of them are a single point failure, but it's pretty ambitious. Why do we want to do this? So we want to build our own slit mask in space. We want to let through just the light on our distant galaxy and not other light, because that would contaminate, that would increase the noise and the confusion. So we can get very, very sensitive. Now, you might think, well, there is no background in space, but you'd be wrong. There's the dipole light, there's scatter light in the instrument, in the telescope. So by having these little apertures, we can get enormously sensitive. And just to show you, we have 4 arrays of these little windows, and we can command them to open. This is an electron microscope image of it. They're tiny, and you can either configure it to have your favorite space agency logo, or perhaps more usefully, you can command on a particular patch of sky, having pre-selected candidate objects, command the shutters to open, hopefully on your distant galaxies, and it then will disperse the light for analysis. And we're, as part of the JADES team, we're working with NIR-CAM. So this is the focal plane of James Webb. So you have a number of different instruments, but critically, as we expose very deep with NIR Spec, we're also obtaining data, building up a deep imaging field with NIR-CAMs. This means it's quite an efficient way of working, and we're able to map a combination of imaging and then follow-up spectroscopy over those patches. We're able to map a field quite intensively and effectively. And we've picked the goods fields, so these are deep extragalactic fields. This is about 10 arc minutes by 15 arc minutes, and we're studying these in great detail. What's great is they have excellent Hubble Space Telescope images. Now you might think, well, James Webb Space Telescope is so much bigger and more powerful. Why are we even bothering with Hubble? The reason is that below 1 micron, we're actually not very sensitive with James Webb. We need that short wavelength data to find these dropout candidates, for example, and many other science goals. So we need a well-studied field. They also have ancillary data such as X-rays that we can chase AGN from. So we've picked these 2 fields to study. And people doing surveys often talk about a wedding cake. So usually you have a tier where you survey a small patch of sky and go incredibly deep. So our deepest spectra are about 28 hours with the prism, reaching about 30th magnitude. So it's quite phenomenal. We're only doing a couple of patches of sky. Each patch of sky, the size of the NIR Spec field of view is about 3 arc minutes, drilling very deep, one of which we've already taken. The data is about to be released in a couple of weeks on the Hubble Ultra Deep Field. Then we're doing a larger number of more shallow pointings in the medium, and this will intercept the rarer but slightly brighter galaxies. So we're sampling different parts of the luminosity function. And finally, we have a wide area as well. And some of our time we're spending on individual objects, about 30 objects, with the integral field unit really dissecting the light in 2 dimensions there. So, as I said, 100 kiloseconds, that's about 28 hours or so on our deepest fields. We also use the gratings to get higher spectral resolution. And then these are the sort of line sensitivities. So we're getting better than, typically better than 10 to the minus 18 in CGS units. Just to give you some context, that's a star formation rate of less than 1 solar mass per year, all the way out at redshift 7 using the H-alpha line, so it's pretty phenomenal. And the imaging mode, it's basically the candle at the distance of the moon. So it really is a very capable telescope. So full disclosure, there are some challenges. So those micro shutters are tiny. They're 0.2 arc seconds across by 0.4. So your astrometry has to be spot on, otherwise you're going to miss the slit. Also, many galaxies at high redshift are compact, but some are not. So we miss some light because it just falls outside the slit. You need to be able to correct for that. So we're working with our colleagues on the imaging, on NIRCam, measuring the morphologies, correcting for that. And I know various people in the audience have been heavily involved with that effort. A few shutters have failed. A few of those 250,000 micro shutters are stuck, so we can't use those parts of the array. Not too many, mercifully. And also there's deliberately in the higher dispersion mode, we let the spectra overlap, so there's a little element of confusion or increased noise, but always with the prism spectra, these short spectra, those are free from confusion. So what are the highlights so far? So in December, we put out the discovery or the confirmation of 4 galaxies at redshifts beyond 10. So this is the first confirmation with spectroscopy. And here we are. So you might be slightly underwhelmed by this, but I'll talk you through it. So what we're seeing, left to right, this is the wavelength. And what I draw your attention to is there's no light to the left of these red lines. So this is the Lyman-alpha break. So below that, the gas in the universe, gas between the galaxies, has absorbed all that light. And it's a colossal break. You see that. And it's very difficult to mimic that through other spectral breaks. People are familiar with Balmer breaks, 4,000 angstrom breaks. So really the only interpretation is that these are high redshift. Now you might think, well, could I not have got that through photometry, just putting a filter here and a filter here? To some extent, yes, this is how we selected them. But you always worry that on the right-hand side, you might be at the mercy of a single very, very bright emission line at low redshift. This spectroscopy tells you immediately that is not the case, that these genuinely are high redshift, and that's the importance. So we've been gathering data since September or October. We've observed the Hubble Ultra Deep Field. We've got 250 spectra, including a large number at redshifts within the epoch of reionization. And we're going to be publishing those a couple of weeks from now. We've already published some. And incidentally, there's going to be a public release of our data as well. And we've also conducted some of the medium tier of the survey. We've got well over 1,000 galaxies so far and over 100 good quality spectra confirming galaxies within the epoch of reionization. And we have quite a good confirmation rate. So just to answer my initial question, had astronomers been lying about these candidates at high redshift? Largely not, that they do come in to a large extent as being genuinely high redshift. So I showed you one with just a spectral break, but here we have a galaxy at slightly low redshift, still pretty high redshift, 9.4. This has booming line emission. Look at that. So this redshift, you might have been uncomfortable just with a spectral break as a redshift. Here, it's incontrovertible. And this is what this looks like zoomed in. There's familiar emission lines here. And we've been doing a lot of science with this, and I'll introduce my team in Oxford. This is part of the wider NIR Spec team, and Roberta in Cambridge also has a large group who we're very actively working with, and many other people as part of the ESA instrument science team. But this is the team working with me in Oxford. So Jacopo Chevallard is an expert on fitting the spectral energy distributions, telling us what the stellar masses are, what the star formation histories are. And I'll introduce the others, Alex, Iman, Gareth and Ayush, when I come to their individual projects. So first of all, Alex Cameron is very interested in the ratios of these emission lines, telling us about the state of the interstellar medium, particularly the metallicity and the ionization. So here we have some emission lines at high redshift. These are stacked now in the rest frame, but going all the way from redshift 9 down to redshift 5 or so. And what Alex has found is people often use the nitrogen 2 line close to H alpha as a diagnostic, and we have a diagnostic plot, and this divides AGN from star formers and tells you a little bit about the ionization mechanisms. But we hardly ever see nitrogen 2. So it's telling us something interesting. We know there's nitrogen in these galaxies. I'll come on to that later on. But the nitrogen 2, this low ionization state, isn't there. It's telling you that you have very high ionization. These things are limits. They're pointing to the left because we don't see the nitrogen 2. These are the stacks. And the grey is what we see from Sloan. That's redshift 0 galaxies. So clearly they're different. Something is different at high redshift. A better plot, this x-axis plots this proxy for metallicity. It's called R23. And the y-axis plots something called O32. That's the ratio of a high ionization state to a lower ionization state of oxygen. Again, our galaxies at high redshift up here, they sit away from the redshift 2 galaxies. So the interstellar medium is different. But they do sit close to some unusual galaxies seen at low redshift. Blueberries, green peas, various other fruit and vegetables. And these are analogues to high redshift galaxies. So in fact, these analogues really do, when we do the spectroscopy, look quite similar. And what's different from the plain vanilla galaxies at redshift 0 is both the analogues and our high redshift galaxies have lower metallicity and very much higher ionization parameter. So Ayush Saxena is working on Lyman-alpha emission in distant galaxies. Now, as I mentioned, people struggled for many years to see Lyman-alpha emission. Just, you know, one in a dozen, 2 dozen showed Lyman-alpha emission. But we have now several that do show this emission line, including one, a redshift 7.3 that Ayush has written a paper on, which is on archive, showing very strong Lyman-alpha, in fact, huge equivalent width. Difficult to explain with standard stellar population models why the equivalent width is so high. So another interesting thing is very often we see a velocity offset of Lyman-alpha relative to the systemic velocity. And that's because in the core of the line, the optical depth of the neutral hydrogen is quite high, and that tends to mop it up or push it into the wings through resonance scattering. In this case, we find that it's bang on the systemic velocity. That's telling you that in this galaxy there's an ionized bubble in the core. So that's interesting. So how did that bubble form? How did it grow? So this is redshift 7.3, and we found a bunch of other galaxies at the same redshift. It's a redshift spike. It's clearly an overdensity. This galaxy alone could not have ionized its own bubble. It needs help, and that help probably comes from this overdense region. So that's work done by Ayush. Now on to Gareth Jones, who's familiar, I think, to a lot of you because was a postdoc with Roberto in Cambridge and now working with me in Oxford. And Gareth has been looking at how often Lyman-alpha emerges in these galaxies. And that's fun because that's basically telling you how much neutral gas there is around. If there's a lot of neutral gas, Lyman-alpha gets absorbed. If Lyman-alpha is able to get out, that's telling you about the neutral fraction of the intergalactic medium. And we're doing this at the crucial epoch around redshift 6 and 7, where we know from Planck and the other CMB missions that there is this transition, this reionization. So we're able to constrain the neutral fraction through a different technique. And Gareth has a paper close to submission on that. And as I mentioned already, Jacopo is helping us understand that from a stellar population synthesis viewpoint. So we're also able to study not only the emission lines, the star formation rates, the metallicities, but the stellar populations of these distant galaxies. And this is work done, I think, probably in the audience, Tobias Lucer in Cambridge, published a paper from the JADES data, the NIRSpec data, where there were no emission lines in a galaxy. Typically we see bright emission lines. In this case we don't. And it seems that in this particular galaxy, star formation is turned off, in fact quite recently, but far enough in the past that the H-alpha and the H-beta and oxygen lines are no longer being excited. And we have evidence for a slight Balmer break here. So this is more typical of sort of A stars, a couple of solar masses also. So this sets the the mass-weighted age of this galaxy to be a few tens of millions of years. So we're catching something post-starburst in this case. So that's an interesting discovery. The other interpretation might be that if it is actively forming stars, and in fact, I picked this galaxy out 20 years ago, 2010, so 13 years ago, I picked this galaxy out from Hubble images on the basis of rest frame UV that it was likely to be star forming. If it is star forming, why isn't there emission lines? And that might be that the ionizing photons are exiting the galaxy without being reprocessed as emission lines. So that might be a high escape fraction. But given the presence of the Balmer break, probably more plausible that we're seeing this post-starburst. So I mentioned already that we can use various emission line diagnostics to probe things like BPT diagram, which tells you whether AGN, but we can also look to see whether there are spectral breaks in the data. I showed you one with the Balmer break, and we can fit the star formation rates and the stellar masses much more accurately than for photometry, because we're able to fit all these spectral features, which are diagnostics of age. And working with my student, Iman Wallace, in Oxford, we've detected quite a few Balmer breaks at moderately high redshift. That's telling you about the star formation history of these galaxies, and that's still ongoing work. So we're more than halfway through our JADES survey. The goal here is to get thousands of spectra of galaxies using NIR Spec. Here, what I've done is I've stacked up 100 or so spectra from the Hubble ultra-deep field exposures. So what we're seeing, low redshift on the bottom, low redshift in this context is redshift 1, and ascending redshift as you go up. What we're seeing is these characteristic emission lines shift to longer wavelengths as the redshift increases. But this is fun. This shaded area, top left, that is the Lyman-alpha break that starts entering our spectroscopic window around a redshift of 5 or 6 or so. This thing here you can just about make out. You see that? That's the Balmer break or the 4,000 angstrom break. They're quite close in wavelength. It's telling you about old stars, evolved stellar populations. Here we have the oxygen lines blended a little bit with H-beta, and here we have H-alpha, chasing this all the way up to redshift 7 or so. And one of the highlights from a couple of months ago is a highly unusual galaxy that we targeted in the Goods North field. It's the brightest Lyman break galaxy candidate at redshift 10. And we got quite a beautiful spectrum of this. So here again we see this Lyman break, so nothing, no flux below that. That's not the edge of the detector or something. This really is, the universe goes completely dark in this region. And then we have this huge discontinuity, and then we have various emission lines of different elements, including oxygen as usual, but also potentially helium, neon, nitrogen, carbon, magnesium. So this is a very rich data set. So I don't want to humiliate Hubble, but I'll just show you the best effort from Hubble here. So this is a slitless spectrum taken by Pascal Ouche, and at the few sigma level, you can see perhaps a spectral break. And on this, very courageously, Pascal identified this as a potential redshift 11 galaxy. And it remained untested for a few years until NIR Spec on James Webb came along. There'd been a claimed detection from the ground of a carbon-3 emission line at redshift 11, but this did not hold up. We were able to disprove this in actually quite a short observation of this galaxy. So on the bottom, this is the Hubble spectrum, and it spans that little bit of our spectrum. Look at the difference in signal to noise, there to there. You know, James Webb Space Telescope is a game changer in sensitivity and in wavelength coverage. And we got a paper out in very quickly, in about a week, on this spectacular galaxy. And we saw Lyman-alpha emission, which should have been illegal at these high redshifts where we know the universe was optically thick to this line. But we saw Lyman-alpha emission. We saw some unusual lines of nitrogen as well. And we saw longer wavelengths of Balmer lines of hydrogen. And that enabled us to conclude that there was little dust reddening through the ratios of these lines. So that's a rogues gallery of these emission lines. And one fun thing about the Lyman-alpha, the galaxy itself is very compact. But Lyman-alpha seems to spread out into a halo. That might be a resonance scattering effect of this line. And the Lyman-alpha, unlike the case of Ioshi's galaxy at redshift 7.3, where I said the velocity offset of Lyman-alpha is tiny with respect to the rest of the galaxy, therefore that galaxy at 7.3 had an ionized bubble. Here we see a significant redshift of the Lyman-alpha. You understand this by the fact that no photons really get out in the core of this galaxy because there's so much neutral hydrogen. It's only when they random scatter to the red wing that they're no longer being absorbed by the Gunn-Peterson effect, the optical depth of the universe. So we saw this, and this was the best example, but various colleagues have observed different galaxies with James Webb, and they see these similar velocity offsets in other galaxies, and this is brightness on or intrinsic luminosity on the x-axis, from very, very luminous on the left to faint on the right. So we are somewhat above, but it's within the scatter of data points. So other people have confirmed that they're seeing similar offsets, but at much lower redshift. We're at redshift 10, we're the record breaker for Lyman-alpha. Other work done at redshift 7 or 8. So this galaxy seems to have low metallicity, this redshift 10 galaxy, except it has some very unusual nitrogen lines, which are very rarely seen. So the nitrogen lines, they've been seen in stacks of low redshift galaxies, very occasionally in individual galaxies. I think Hannah Ubler is probably in the audience, found one with NIRSpec, which is probably an AGN. If this is a star-forming galaxy, we need to invoke some weird metallicity. Not only metallicity, some weird chemical enrichment of oxygen. And Alex Cameron wrote a paper shortly after we published our NIRSpec data, saying that the long timescale typically expected to enrich nitrogen with stellar winds requires a lot of fine-tuning, but you might be able to achieve this through some runaway collisions or tidal disruption event. So it's still an open question, and we published the paper in February, and since then, almost every week on arXiv, there's been another idea. One thing that we want to entertain the possibility of is that this might be an AGN. So we have some high ionization lines, although things like the helium-2 and carbon-4 are somewhat weak. We don't see nitrogen-5, but we do see high ionization lines such as nitrogen-4. The lines are reasonably narrow. For an AGN you would expect broadened, but they are resolved with the medium dispersion grating. And it seems that the line ratios, particularly of the nitrogen, it's a multiplet that tells you about the density of the gas from which these lines are being emitted. It seems that is consistent with the gas being very dense, which might suggest a broad line region of an AGN. We also see in the carbon-4 a P Cygni light profile. This is often seen in outflows from both starburst galaxies and also AGN. The velocity offset is perhaps more consistent with being an AGN. But I think Roberto's just put a nice paper out on the arXiv listing the evidence that is consistent with being an AGN. So I think that's certainly a very interesting interpretation. So just to, my last few minutes, summarize where we're up to. So we've spectroscopically confirmed the most distant galaxies done. We're getting H-alpha and H-beta, so we're getting robust star formation rates for these galaxies. We're able to measure stellar populations through things like the Balmer breaks and chemical enrichment through the line ratios of emission lines. So still on the to-do list, we want to find the first galaxies that formed. So those are ones that don't have metal lines, because they just formed from hydrogen and helium. There's much debate in the literature whether this is even possible, whether the enrichment timescales are so short or these first galaxies are so faint that we don't see them. But we have our watching brief. Every spectrum comes in, we comb for the signature of the so-called population 3. One thing that we are addressing at the moment is reionization. So in particular, we are interested in the fundamental question, do galaxies reionize the universe, or do we need some other source, for example, AGN? So we're able to get very accurate redshifts, but one thing that we can also do is try and get an estimate of the escape fraction of ionizing photons. So we can't see this directly because the ionizing photons, those are photons below 912 angstroms, more energetic than the ionization edge of hydrogen. They are mopped up, if not in the galaxy, then by the surrounding intergalactic medium. We never see them directly. But we can see them be reprocessed as the various Balmer lines cascading through the energy levels of hydrogen. And we can also measure the ultraviolet spectrum above Lyman-alpha, so how blue something is, and then a bit of a leap of faith and extrapolation of that spectrum below the ionization edge gives you a total budget of ionizing photons formed. So if you're able to compare that budget of ionizing photons generated with the number of photons which are captured and produce recombination lines of hydrogen, that difference should tell you how many of the ionizing photons get out into the intergalactic medium away from the galaxy and do the universe some good by producing ionizations. So we can attempt this, and this is just a schematic where we're seeing the recombination lines of hydrogen. We also have a spectral slope, enables us to estimate the total production rate of ionizing photons. And this is work in progress. I've been working on this over the last few days by plotting the H beta, that's one of the emission lines of hydrogen, the equivalent width of that, against the UV slope, that's telling you something about the production of ionizing photons. As work by Zachrison a few years ago claimed that this would be a good way to measure the escape fraction. So what's going on? So if you have a high escape fraction, annoyingly this plot is plotted backwards, so I took it from the original paper. So high equivalent width is on the left, low equivalent width on the right. So you can imagine if you have a high escape fraction, you don't get local gas around the galaxy reprocessing the ionizing photons. So even if you've got a lot of ionizing photons, you see very few recombination lines. So you'll sit on the right-hand side of the plot, and this blue region would be a high escape fraction. Alternatively, if what they call case B, all the ionizing photons are mopped up locally by gas, you get a large equivalent width, and they sit on the left-hand side of the plot. These are our galaxies. So these are all consistent with being, except perhaps one, quite low escape fractions. But embarrassingly, they sit in a part of the plot that is not populated by the theoretical data. So that's instantly a puzzle. Why are these spectral slopes so blue? And importantly, why are the equivalent widths of these lines so high? So that was not expected. So if you play around with the particular extinction law, this changes slightly, but the bottom line is that what we see is consistent generally with having a low escape fraction, and perhaps embarrassingly, it occupies a part of the plot that isn't populated from the simulations. So something fundamental is different about these high redshift galaxies. So I'll move on to my conclusions. So the main one is JWST truly is delivering after a hugely long wait and great expense. I think it's worth it. You know, we are now routinely confirming galaxies well within the epoch of reionization. And we are testing things which have haunted my field of extragalactic astrophysics, claims in the literature of something having red colours and plausibly being high redshift. We now turn this into a real science by measuring spectroscopically these redshifts for the first time. And in fact, our success rate is pretty good. So all that work we did for 2 decades on a wing and a prayer from photometric redshifts turns out largely to be correct, the luminosity functions. But there are some puzzles, the blue colours, I showed you those spectral slopes, the high ionization parameters. And we found a remarkable spectrum, unusual, hard to interpret, of one galaxy at redshift 10.6 with unusual nitrogen lines and Lyman-alpha in emission. we've been able to take the first few steps in addressing the role of galaxies in reionizing the universe. You will have inferred that we don't have a punchline yet on that. The escape fraction in many galaxies appears low, so we'd have to have various things conspire to have galaxies being the prime driver for reionization. This is ongoing work. So we've got a lot to look forward to. In the next few days, beginning of June, we're going to do a big data release of the Hubble Ultra Deep Field spectra and imaging. So watch this space for that. And hopefully there'll be, we've already got some papers out, there'll be more coming out on that timescale. And I want to give credit to the other surveys as well. There's a lot of great work, particularly the Treasury surveys. I'd highlight things like SEERS, which are made public immediately, and a lot of other geo programs doing great work. So this has been a game changer in astrophysics, and I think the next year or two is going to be enormously exciting. Thanks very much for listening.